We've spent the last few years running on a single architectural paradigm, and it's starting to show its seams. Transformers dominate generative AI, but their core mechanism, self-attention, comes with a hard computational ceiling. The attention matrix grows quadratically with sequence length. That means doubling your context doesn't just double the work, it quadruples it. For long-form reasoning, document analysis, or continuous streaming, that quadratic scaling becomes a bottleneck that's expensive, slow, and increasingly impractical to ignore. This is exactly why state space models have moved from academic curiosity to a serious contender in modern AI. At their core, state space models borrow from classical control theory. Instead of computing pairwise relationships between every token in a sequence, they treat the input as a continuous signal and project it through a hidden state. That hidden state acts as a compressed memory, summarizing everything the model has seen so far. The math starts with a continuous time linear differential equation, where you have a system matrix that governs how the state evolves over time, and an input matrix that maps your tokens into that state space. But neural networks operate in discrete steps, so we have to discretize that continuous equation. The standard approach uses a zero-order hold, which essentially samples the continuous signal at fixed intervals and holds the value constant between steps. This gives you a discrete transition matrix and a projection matrix that let you update the hidden state with each new token. The result is a linear time update. Every new token only requires a single matrix multiplication with the previous state, plus a small projection. No attention, no pairwise comparisons, just a rolling state update that scales linearly with sequence length. Early state space models had a major limitation, though. The transition and projection matrices were static. Once trained, they applied the same transformation to every token, regardless of context. That worked fine for simple pattern matching, but it struggled with complex language where certain words need to be remembered for thousands of tokens, while others should be forgotten immediately. Mamba solved this with a selective scan mechanism. Instead of fixed matrices, the model dynamically computes new A and B matrices for every single token based on the current input. This turns the state space model into a content-aware system. It can selectively retain long-range dependencies or discard irrelevant information on the fly, all while maintaining linear computational complexity. The real breakthrough isn't just the math, it's how it plays out on hardware. Self-attention is notoriously memory bandwidth bound. You have to read the entire context window repeatedly, which bottlenecks even the fastest GPUs. State space models, on the other hand, are compute-bound. Each step only touches a small, fixed-size hidden state. That means you can process tokens in parallel during training using a highly optimized parallel scan algorithm. But during inference, you stream through the sequence one token at a time with minimal memory traffic. The result is dramatically faster generation speeds, lower VRAM requirements, and the ability to handle context windows that would completely choke a transformer. This isn't about replacing transformers overnight. Attention still excels at dense, short-range reasoning and tasks where global context is strictly necessary. But for long-context applications, continuous data streams, and edge deployment, state space models offer a fundamentally different trade-off. They prove that you don't need quadratic scaling to maintain strong representational power. The architecture is still maturing, and researchers are actively exploring hybrid approaches, better discretization methods, and nonlinear state evolutions that push the boundaries even further. If you want to see how this plays out in practice, I highly recommend digging into the original Mamba papers and the follow-up work on structured state space models. The math is rigorous, the implementations are open, and the implications for efficient AI are already reshaping how we think about sequence modeling. The transformer era isn't over, but it's no longer the only game in town.